All right, thanks everyone for coming back for the third part of these tutorials on magnetic nanoparticles. And today we're going to talk about characterizing magnetic nanoparticles. We are putting these recordings on YouTube, so if you don't want your voice to be heard in the recording, don't ask a question, but otherwise please do ask a question. That would be great. Now there's a caveat here. We're going to talk about experiments and what they tell us, but I am not an experimentalist, so I'm sure you guys on the call will actually have some insight to give me. But I have spent a lot of time looking at real data and trying to understand it and try to give us simple analysis tools to help extract important information about magnetic nanoparticles. Now, I'm going to refer you to two articles which you guys are probably already familiar with. The people on the call at least are already familiar with because they feature the two groups that are sitting in on this call. So Carlos's group and Thompson's group. These are chapters that I know I use all the time to understand how to characterize magnetic nanoparticles in a really user-friendly format. Okay, so what may we want to know? I've broken it into 4 pieces so that we can keep track of where we are in this this tutorial. So firstly, we might want to know something about the particle size. Secondly, we might want to know the saturation magnetization. So that's if all the atomic dipole moments are pointing in the same direction, what magnetization value do we get? We might want to know how strong the particle interactions are, the dipole-dipole interactions, and what the effective sign is of that. And we might want to know something about the anisotropy barriers, and anisotropy is something we've talked about in the previous 2 parts. And why we might want to know about those 4 things, let me just give you one example to motivate it. For example, if we're trying to do hypothermia with our magnetic nanoparticles, we want, and I'm using very broad terms here, we want large saturation magnetization, we want a moderate anisotropy to generate the most heat, and interactions may help or hinder, it depends actually. So there's a lot of literature out there about how interactions can help hypothermia or hinder it depending on how particles have assembled. So you can see just from this example that we want to know these characteristics of magnetic nanoparticles to see if they're suitable for particular applications. Okay, so let's start with particle size. And commonly used techniques include transmission electron microscopy, or TEM, and scanning electron microscopy, SEM. And here's an example. This is a TEM image taken from Sarah Fitzgerald's PhD dissertation at University of South Carolina. And these are some magnetite nanoparticles that have been immobilized. And so we can look at each one and put a little bar across and figure out what size each of them is, what diameter each of them is. You can see here, there's a scale bar of 100 nanometers. So with this TEM image, we're definitely getting resolution down to a few nanometers, which is great. So we can take a picture like this and then do some image analysis, whether it's manual or if we have some automated software to do so. And so we can take from that picture and we can convert it into a histogram of sizes. So I've made here a plot with diameter in nanometers on the x-axis, and there are some bins here that each one is only 1 nanometer wide. And then I've got the number of nanoparticles I measure from that image in each of the bins. So, you know, down near 0, there's none, that's good. no tiny nanoparticles. And then around 7 nanometers, we start to see particles. And there's a peak at between 9 and 10 nanometers for the diameter. So this gives us a nice feeling for what the size distribution is in the sample. We can calculate things like the mean size and the standard deviation and so on. Now, an optional step here, once we've got this size distribution, is we can fit to it with a log normal distribution. Now, this is optional in some sense, because if you have the histogram that I showed before, you have all the information about the size distribution in your sample, and you can do analysis using that size distribution. But if you want something analytic to use in calculations or subsequent analysis, you can fit what's known as a log normal distribution to the data. You can see the log normal distribution isn't perfect because, for example, there was a second little lump up here around 17, 18 nanometers, which the log normal distribution can't capture. I'm not going to give you the formula for the log normal distribution, but you can find it in those chapters that I mentioned earlier, and we can talk about it more in the question time. But you can see it kind of looks like a normal distribution, as the name suggests, but it is a little skewed because obviously we have more particles at high diameter than at low diameter. Okay. Now, some notes on extracting particle size from TEM. Firstly, the immobilized particles may be different to when they're in fluid. I think this is a little bit of an unknown. Like when we immobilize them, do we fundamentally change, for example, the structures that they're sitting in? And obviously, we're only measuring 2 dimensions by having this 2-dimensional image. We don't know what the particles are doing in the third direction. It's possible to measure the magnetic core size, subtracting the ligand. So that's good because we might want to know the magnetic size, not the hydrodynamic size. And I'll talk about hydrodynamic size in a second. And another note is beware of the log normal size distribution. I have been caught out by this, and a PhD student, Sarah, in fact, called me out on it, which was really good. I had made a mistake in my analysis. The log normal distribution is surprisingly cumbersome to use. So, for example, the mean and the mode size are sometimes used interchangeably, but they're actually different. And if you do a distribution of particle diameter, it is different from the distribution of particle volume. So I'm just giving you some words of warning here, rather than taking you through all the subtleties, but just be aware that there are those little things that catch people up when using a log normal size distribution. Okay, another way to measure particle size is dynamic light scattering. This works in fluids. And this measures the hydrodynamic size of particles, which we've talked about previously in the tutorials because it's important for understanding Brownian relaxation times. This technique actually relies on that Brownian motion in solution. So this is a picture I've taken from Wikipedia. And this picture has large particles and small particles. And a laser is shone at these particles. And looking at the scattering intensity as a function of time, we can see that this intensity pattern on the top is quite slowly varying, compared to the small particles, which has an intensity which is varying quite quickly. And the fact that those variations are happening much faster here is an indication that these particles are smaller, and so their Brownian motion is more rapid, okay? So people can take these sorts of intensity versus time plots and process them to understand or get an estimate for the hydrodynamic size of particles. All right, let's move on to looking at saturation magnetization and how we can get this out of samples. We've talked a lot about magnetization. I haven't used that word saturation before, so let's make sure we understand what that is. So I think I said earlier that saturation magnetization is if all those atomic dipoles could be lined up together, we get our maximum possible value for the magnetization. And a way that we can extract this is by doing magnetization versus static applied field measurements. And the more static applied field we put on, the more those moments try to line up with the field. And so we can start probing the saturation magnetization. And I've got a plot to show that in a minute. These measurements can be performed, for example, using a SQUID or a VSM magnetometer. SQUID stands for superconducting quantum interference device, and VSM stands for vibrating sample magnetometry. And so we have these typical ways that we can measure magnetization versus applied field. So here is my theorist's rendition of what this plot might look like. We have magnetization on the y-axis, and we've got applied field on the x-axis. And what you'll notice, as I said, is when we put on a large magnetic field, we can see the magnetization gets to a very large value where all, on an atomic level, all of the dipoles are starting to line up, or all of the moments are starting to line up. And you can see it, this plot is trying to flatten out. This blue line is trying to flatten out. If we could extrapolate, see where it's asymptotically approaching, that is our saturation magnetization. We never actually get to full saturation in reality because we always have a system at finite temperature. So we always have that atomic jiggle that we've been talking about the last two parts of the tutorial series. So we never get to saturation. So it's a hard term to, you often read in papers, people are like, the saturation magnetization is this. And I'm like, well, you can't measure it. You can't know where this is flattening off. But we can get pretty close. When it's effectively looking flat, we can say, okay, that's the saturation magnetization. Now, you might have also noticed with this plot, and we'll talk about this in a little bit or in the next couple of slides, this curve for magnetization for applied versus applied field has this opening, which is quite interesting. But we can understand that in terms of some of the concepts we've developed in the last two parts. So this plot of magnetization versus applied field is one where we're probing the particles at low temperature. And if you remember back when we're at low temperature, we know that the magnetic dipole moment, the macrospin moment of a particle, is blocked. So the macrospin moment gets stuck in an energy well due to the anisotropy. And this helps explain this plot here. So here, I should have put some arrows on this plot, but here we're reducing the field, for example, and we come down this way. Even though we're at zero field, the magnetization is still positive because the particles are on average stuck upwards. Okay, that sort of matches my little schematic or cartoon above here. And then if I apply a large negative field, eventually I can overcome that anisotropy energy barrier and the magnetization reverses. But then on the way back, I get stuck downwards instead. So this is a result of having that anisotropy barrier and having a blocked state for the particle. And we say the system has a memory. The system remembers what the applied field was in the past. All right. So if we look again at zero field, there's two possibilities here in this graph for what the system is doing. And those two possibilities, which one you're in, depends on the history that you've gone through. We've talked a little bit about this as well. The area inside the loop corresponds to the work that has been done by the field during one field cycle, and that can be correlated with heat. Okay. If we instead go to high temperatures and look at magnetization versus applied field, then the curve now has no opening. And we say that the curve is reversible because it looks the same going upwards in field as going downwards in field. So this is a reversible curve. There's no memory. And what's going on is now we're in the super paramagnetic regime. And you might remember this cartoon from previous episodes where the moment is fluctuating all over the place. But if we put on a field, say in the upwards direction, we bias all those fluctuations. And on average, the moments are pointing upwards. As I said, this is the super paramagnetic range. the net moment follows the field. And I've also added on this plot an example of when I'm measuring particles at a slightly colder temperature and a slightly hotter temperature, but still inside that superparamagnetic regime. Okay, now we're going to extract more information out of plots like this. I should say that these curves, these reversible magnetization versus field curves, can be predicted using what's known as the Langevin function. Has anyone heard of the Langevin function? You can put your hand up or yell out, or, oh, yep, good. Very good. It's a simple derivation. You can actually give it to third or fourth year physics students to derive, but I'm just going to give you the result. So here's our result. This is magnetization. It's normalized by the saturation value, and it depends on the applied field as we expect, and it depends on the temperature of the sample. So this Langevin function predicts these curves, these S-shaped curves. Now, this S-shaped curve can be a little bit cumbersome to deal with, but if we look close to the origin, we can notice that the magnetization has approximately a linear behavior with field. And we like lines in science because we can fit to them very easily and we can extract information easily. In that region, the Langevin function can be approximated very well by this simple expression. So you'll see the magnetization is linearly proportional to the applied field, and the constant of proportionality depends on a physical constant, the saturation magnetization, the volume, or probably the mean volume of the sample, some more constants, and temperature, okay? So we can take these curves, we can fit a line through them and be able to extract out magnetization, saturation magnetization. All right, I want to now turn this upside, I want to talk about susceptibility. And susceptibility is the rate of magnetized increase with an increase of field. And we're typically only interested in this in that linear regime. So this is basically giving us that slope that we saw on the previous page. So this is what I was saying, we can extract out the saturation magnetization from this. But I want to turn it upside down. So this is 1 on the susceptibility. I've just turned upside down this simple algebraic equation. I've got 1 on chi, the susceptibility, and I mean, it's trivial to turn it upside down. So what do I gain from this? What I gain from this is a function which is predicted to be linear with temperature. And this is so important, it's given a name. This is Curie's law, named after Pierre, not Marie. And so I can make a plot of 1 on susceptibility using those magnetization curves that I've shown on the previous slides. And then I can plot the results versus temperature, and I predict that I should get a straight line, and I should get a line that goes through the origin. So this red line is showing 1 on chi versus temperature that we predict. But spoiler, we often don't get that it goes through the origin. Actually, usually we get that it doesn't go through the origin. So we get something like this. Here's my black points here. This is what I'm actually getting from a simulation for 1 on chi. This isn't experimental data. This is simulation, but it's similar. So 1 on the susceptibility versus temperature. Now, Langevin's function and the Curie law, they're only valid at high temperatures. So I only have business fitting a straight line up here. But when I do that, you'll see that the intercept is not at the origin. Okay, that's the main thing I want you to take away from that. When Curie's law is shifted like this away from the origin, it's known as the Curie-Weiss law or the Curie-Weiss fit. And this is actually taken from work on magnets that isn't magnetic nanoparticle work, but is well known. And the common assumption is that this shift away from the origin must be because there is some other effective field in the system besides the applied field. And the common assumption is that they are the dipolar interactions that are giving rise to that shift. And that's how we typically fit it. This gives us a feeling for the size of the interactions in our system. So we're going to call this shift from the origin the interaction temperature. And I have done this. I'm sure people on the call have done this. We are doing some work at the moment with simulations to show that maybe it's not all due to the dipolar interaction. So maybe we need to revise this. But at the moment, this is something that works for us to estimate the size of the dipolar interactions. And we can also get out the sign of those interactions, because this interaction temperature here, it's positive, but there are situations where it comes out to be negative as well. All right, that was a lot. That was the most maths we've done in the 3 parts. So I hope you followed. I think we had 3 or 4 formulas there. Let's go back to not having any maths for a little while. So our next quantity that we might want to extract from experiments is some information on the anisotropy barriers. And a way to probe those anisotropy barriers is to look at zero field cooled and field cooled magnetization versus temperature measurements. And I'll take you through what those are in the next slides. There's also another method for probing anisotropy barriers, which is dynamic magnetic susceptibility, which I'm not really going to talk about in any length, but I wanted to put it up there because it works quite well too for this purpose. Okay, so a zero field cooled measurement, what we do is we cool a sample of magnetic nanoparticles in zero field, then we heat it back up in a weak field, say 10 Oersteds, and I'm using CGS units here, which is very bad. We talked about that last time. But anyhow, we heat up in that field, and this is the sort of curve that we got. So it was a video to try to show what was going on here. The SI equivalent of that small 10 Oersted field is about 1 millitesla. Right, so what happened was you can see that the moment of the sample, this is a normalized moment. So I've normalized the magnetization by the saturation to get a number between 0 and 1. It's almost 0. And then we go through this transition region, and then the magnetization decays again. And I'm going to explain these 3 regions with a nice picture on the next slide. So just wait for that. Before I do, though, I want to talk about the corresponding field cooled measurement, which is, again, we cool the sample in a weak field this time, and then heat back up in that same weak field. So this time we get a net moment at the start of the measurement, because we've cooled the sample in a field, which has helped polarize all those moments, set them with some net moment upwards. So this is our zero field cooled and our field cooled, and at some point they rejoin each other, because at some point the history doesn't matter and just the field that you're in matters. Okay, so I promised we'd explain these 3 regions. So here is my picture. Down at the low temperatures, we have the blocked region, which we've talked about multiple times. And because the particles are blocked, because they can't escape local energy wells, we see no great change in the magnetization as we heat up. Then we get to sufficiently high temperatures that thermal jiggle is becoming sufficient to send some of the particles over their energy barriers. And so the moment here in the zero field cooled case starts turning on, because some of them can escape their local energy wells and start lining up with the field. So we see this turning on here of the moment. And then after that's all happened, and we've had all these fluctuations that take us over energy barriers, at high temperatures, we enter the superparamagnetic regime. And here the thermal fluctuations are completely dominating. We have moments that are fluctuating everywhere, but can, on average, point towards the field direction. The magnetization decays with temperature, because as we get hotter, we get more fluctuations and we don't care about the field as much. And this is the area where the Langevin function does a good job at fitting the magnetization. So that's the 3rd region. you'll notice that the transition region is quite broad. And the reason the transition region is smeared out like that is because we have, in any real sample, a particle size distribution. So the small particles typically become unblocked first, and then the medium-sized ones, and then finally the big ones. So there's this broad region over which particles become unblocked. Even in a sample with no size distribution, we see a broad transition region. And that's because this is a stochastic process. This is a probabilistic process. So some particles will go before other particles, even if they're exactly the same size. So we see this broadening due to probability, but also because of the particle size distribution. But you can see this is going to tell us something about anisotropy, because when I become unblocked, at what temperature I become unblocked, has to be directly related to how big those energy barriers are. So we define something, I haven't talked about the title of the slide yet, so I probably should. We define something known as the mean blocking temperature, which is T subscript B. And we should be careful to always say mean blocking temperature, I think, because depending on the size of the particle in your sample, each particle will have a different blocking temperature. The mean blocking temperature is the average temperature at which particles become unblocked. So it's in this region here. So let's do a little poll. Let's do this for fun, and hopefully we all get the answer right. Oh, I've already done that one. Where is the mean blocking temperature? Let's see what we think. So part A, I've sort of biased the results here. Part A is at the zero field cooled peak, you idiot. Part B is to the right of the zero field cooled peak. By peak, I mean this little bump here. And part C is to the left of the zero field cooled peak. So do people want to vote for A, B, or C? You can put it in the chat and Carlos can monitor and he can tell me what people think. Vote now. This is where we just find out if people are still awake, you know. There's one comment in the chat. Two. Oh, good. 2 people awake. Excellent.
So people have indicated that they think it's C.
They think it's C, to the left.
Two votes for C and everybody else is quiet.
Oh, come on.
Oh, there you go. 1 for B, 1 for B.
Okay. All right. So the answer is to the left of the peak. So if our small particles are unblocking down here near 20, our large ones are unblocking up here near 30, then the mean is going to be in between. Okay, so this is our mean blocking temperature. And this is something that several groups have studied over the past 20 years. My group was not the first at all to highlight this, but it's been slow to uptake in the literature. And there's a couple of reasons why it's been slow to uptake in the literature. Firstly, the peak is just so beautiful. I mean, you just want it to be the blocking temperature, don't you? But the second reason people often think it's at the peak is because when you look at the fitting mechanism people use, it says that we are unblocked or we are blocked and then we are unblocked. And those are our only 2 options. And the transition from those 2 behaviors should be a peak, okay? But it's not quite right, because in any real system, we have this stochastic nature and we have a size distribution. So our mean blocking temperature is actually to the left of the peak. And I think, I mean, many of you have heard me say this before, if we can get more people just to take it as to the left of the peak, we're going to be doing better analysis of magnetic nanoparticles. So it's not at the peak, it's to the left of the peak. And there's more information of how you can extract it, but I think that's enough for now, is just to know that it's to the left of the peak. All right. So how do we extract the anisotropy constant from this? Now we've got this blocking temperature, which gives us a feeling for the size of the energy barriers in the system. How do we get our anisotropy constant K out of that, which you may remember has units of joules per meter cubed from our chats 2 times ago. So what we do is we have this formula for the mean blocking temperature as a function of the anisotropy barrier, K multiplied by the volume, divided by Boltzmann's constant, K sub B, natural logarithm of these funny taus. So let me tell you what the taus are. Firstly, V is the mean volume, and tau M is the measurement time. So depending how you're taking these zero field cooled measurements, there could be a different characteristic measurement time, but it's usually on the order of 10 or 100 seconds. And then tau naught is the attempt time for a particular magnetic nanoparticle. And we've talked about this a few times ago in part 1 as well. It's typically taken as 1 nanosecond. And we can actually calculate it to more accuracy than that. And I can point you to the formula to actually calculate it with more accuracy. But the reason we get away with saying, it's about 1 nanosecond is because it's in this natural logarithm. So because it's in a natural logarithm, we only really need to be in the order of magnitude, and we don't change our result dramatically for the blocking temperature or the anisotropy constant, depending what thing I'm trying to find. So to sort of summarize it, to bring it all back together, we measure the mean blocking temperature using this technique. All the rest are kind of constants we know, and so therefore we can come up with the anisotropy constant. We do have to have a feeling for the volume to do this. And so that's why we typically have to have done some measurement of the magnetic volume using some other technique in order to isolate K here. All right, so here's a summary, and I think I've gone 32 minutes, so we've got plenty of time for discussion. Particle size we can get from electron microscopy or dynamic light scattering. Saturation magnetization, we might want to look at magnetization versus applied field curves. Particle interaction strength, I think that's the biggest stretch in terms of theory, but we can look at low field susceptibility and do some analysis on those plots to try to extract some information about particle interaction strength. And then part 4, we have anisotropy barriers that we might want to know about, and we can get to those using what's known as zero field cooled and field cooled magnetization versus temperature curves, and also dynamic susceptibility, which I haven't talked about today. So before I take questions, I just wanted to thank all of my colleagues that I've worked with on magnetic nanoparticles, and also Carlos for suggesting that we do this and for hosting it. I'm very appreciative for that. And then finally, I want to acknowledge that the first time these tutorials were given was at the 13th Magnetic Carriers meeting in London in 2022. And thanks everyone for listening and being part of this recording.